So let's go ahead and get started. I wanted to thank you all for coming. This is our second lecture in our Nobel lecture series, keynote lecture series sponsored by NERSC. We have Dr. Washington here, and I guess as soon as I became NERSC director, one of the first emails I'd gotten was from Dr. Washington saying, "Oh, please come out to NCAR." I think he wanted to make sure that I wasn't planning to do anything crazy. And so I'm hoping that I reassured him that nothing odd was going to happen, too odd at least. And so anyway, I had a great visit at NCAR, and I really appreciated that. Certainly a very beautiful location. So we're very pleased that you came all the way out to give this lecture. Dr. Washington is a very distinguished lecturer. He's a senior scientist at NCAR in Boulder, Colorado. His group uses state-of-the-art climate models to study present and future climate change. He is engaged in research for more than 50 years. He's had the presidential appointments under Presidents Carter, Reagan, Clinton, Bush Jr. More recently, he served on the National Science Board, which governs the National Science Foundation from 1994 to 2006, and he was chair from 2002 to 2006. He has over 150 publications and co-authored with Claire Parkinson a book considered a standard reference on climate modeling. Dr. Washington has many awards, including being a member of the National Academy of Engineering, president of the American Meteorological Society, a member of the American Philosophical Society, and a fellow of the American Academy of Arts and Sciences. He has honorary degrees from Oregon State University, Bates College, and the University of Massachusetts, Amherst. In 2010, he was awarded the National Medal of Science by President Obama, the nation's highest science award. In addition to serving on many boards and committees, he's presently serving as the chair of the National Research Council's Review Committee for the U.S. Climate Change Research Program. So thank you, Dr. Washington. Let's welcome him.
Thank you very much. It's a pleasure for me to come. Can you hear me okay? Good. I'm going to try to summarize a lot of different things in this talk. I'll be covering quite a bit. A brief history of climate modeling, the brief discussion of computational methods, environmental justice connected to environmental change and climate change. Then I'll talk a little bit about the history of how things, such as the U.S. Global Change Program, started. You probably might be a little interested in, I built a climate model that ran in the White House secretly. And then the future of the U.S. Global Change Program, which funds a lot of the research for the Department of Energy as well as NSF and other agencies. And then I'll say a little bit about the National Climate Assessment, which was announced at the White House a couple of weeks ago, in which I had a chance to take part in. So let me get started here. I'm going to show two fairly recent NASA satellite videos, which gives the insight to how the climate is changing and the and the interaction of the vegetation on the carbon cycle. The reason I show this is that we haven't really had global coverage of a lot of the things that essentially go into climate modeling. And I think that the satellite observations are going to be even more important in the future. Here you're seeing the concentration of CO2, and superimposed on this up and down slide or graph essentially shows the Mauna Loa CO2 concentrations. And the first thing to kind of observe is there's a growing trend over the years 2000 up to 2009, and this trend is still going into the future. or up until the present, I should say. Now, trying to understand this seesaw pattern requires understanding something about vegetation. And I show this in the next slide, where in spring and summer on the planet in the northern hemisphere turns green, and you take CO2 out of the atmosphere. Then in fall and winter, the vegetation dies back, and you give carbon dioxide back to the atmosphere. So for the first time, we're able to kind of see this in a much better detail. And so on the relationship between atmospheric carbon dioxide and the vegetation changes can now be pinned down in a much better way just by looking at this on this data. Now a little bit about climate NERSC system. On the laws of physics and chemistry and biology, I'll point out that on the laws of physics are basically the Navier-Stokes equations for those who are physics people, and the chemistry ones are still relying on knowing what the reaction rates are in between the various chemical species, how they interact, and so forth. But on the transport is basically handled in a way that, as the physics is and the dynamics. On the biology, on the equations aren't quite as firm, so we're still struggling with trying to to figure out all of the different mathematical expressions of how these processes work. So on the equations that govern on the dynamics of the atmosphere, ocean, and to a certain extent vegetation and sea ice. I should have added even glaciers. And the equations have been known for some time, and I'll come back to that. The physical processes that we include are precipitation, radiation, both solar and terrestrial, vegetation, boundary transfers of heat, momentum, and moisture to the Earth's surfaces are included. And the forcings are greenhouse gases, the volcanic eruptions, and they're putting aerosols into the stratosphere and the troposphere, and also solar variations are included in our models. And the first person to articulate these equations was V. Bjerknes in 1904. He was a Norwegian scientist, and he never actually wrote down the equations. He just talked about them in principle. He was more of a classical the physicist, and he knew that these equations, essentially on the Navier-Stokes equations, could be solved. And they involve not only horizontal and vertical space dimensions, but also time, which is on the left-hand side. And so on the first attempt at solving these equations was by L.F. Richardson, a British scientist who was a Quaker, didn't want to take part in World War I in a combative way, but he worked for the Red Cross. And the wars or the battles in the World War I were episodic. So there wasn't much action, and then there would be a fierce action for a few hours or a few days, and then he would have lots of free time. So he had a hand calculator, and he mapped out how to solve these mathematical equations and solved them for a small region in France. He made a mistake or two in his calculations, but his mathematical treatment was very elaborate, and he wrote a book about how he solved these equations. And that was the first attempt. Now, since the forecast that he made for just a few hours turned out not to be very accurate. So a meteorologist said, gee, that was a heroic attempt, but we're not going to try to solve that equation by hand like he did. And nothing happened until the World War II, and then there was a scientist who from MIT, or he went to MIT after that. His name is Jules Charny, and he actually reformulated these equations so that they were much simpler, and he took a simpler approach, and he showed that after a one-day forecast that it's possible to make a weather forecast as good as an experienced forecaster using graphical techniques. So on that launched essentially weather forecasting. And then over here is Norman Phillips, who took those same equations on the first electronic computer, the ENIAC, and he put in a simple heating function where you would heat up the atmosphere in the tropics and cool it in the polar regions, or in the polar region, and he found he could generate circulation systems like what we've seen in our present-day climate models. So on that launched the climate models, and and through the work of John Van Neumann, who helped set up the computing center at Princeton, we've advanced on the science. Now I got involved. Now all this happened in the late the early 1950s. In 1959, I was invited to come visit a very small group at Stanford, and as a summer job. And I said, "Hey, this is pretty neat stuff." And so I asked, where could I go to get a PhD in this area? And they said, oh, you can go to Penn State, and you can go to about 2 other schools that were getting started in this. And then I arrived at NCAR in 1963, and I was one of the I was part of the 4 groups that were actively getting started on doing climate modeling. So I've been at it for a long time. And here I just show in a very schematic form on the sort of processes. And I won't go through this in any great detail. But in the early days, we just wanted to have the simplest type models, because when we ran on our earliest computers, which is the 709, it took 1 day to calculate 1 day of weather. And so if you want to do a month forecast or climate simulation, that would be 30 days. And that would be a 1-month forecast. So we met every day, but progress is rather slow. I'm very pleased that the computing technology has advanced faster than the models were able to execute. But the basic elements are the solar radiation that is absorbed in the atmosphere and at the Earth's surface. We include clouds, stratus, cumulus, and cirrus clouds. We have snow. We have glaciers, and we have aerosols. We have outgoing heat out to space. And these two have to sort of balance each other. If they're out of balance on the planet, either warms up or cools off. And we have ocean model that, and I'll show some examples of that. We have a land surface model, including many different species of plants and even some the vegetation and ecological components. And we include the human urban effects in some of our models, and we we also include stratospheric processes. So you can imagine that we've thrown in virtually everything that we think is important. And I think that we've made great progress over the last 50 years or so. And just to sort of show at the time that I got started, we had simple atmospheric models and land surface models and simple ocean models. 1970s, we coupled on the models, and we included sea ice. And I'll skip over here to the last one, where we've had improvements in all of these aspects are the components. We included sulfate aerosols, carbon aerosols, dust, and sea spray, and carbon aerosols, interactive vegetation, the biochemical cycles, and ice sheets will be coupling into our models in the future. And in the early days, we essentially used latitude, longitude grid systems. And they had the problem of having lots of resolution right near the poles, more than we would like. But it was a simple sort of geometry of latitude and longitudes. So we stuck with it for maybe 10 or 15 years. And now we're going to different other grid systems, such as a cube sphere, or the model that has a regional focus, such as here over, say, if you want to put it over U.S. or the poles or whatever. And we're also looking at schemes such as the spherical or geodesic isohedral grid systems. On this grid system such as this, where you use finite elements, seems to be winning on the competition, although all of these schemes work reasonably well, and we can do various kinds of intercomparisons. So we're hoping for the next IPCC assessment to use the grid system that'll be roughly 25 kilometers. So you can see when you get down to this resolution, when you're getting down to the sub-county level of detail. And the thing that you get out of it is a better treatment of the coastal areas, because you can put in more detail. Also in the mountainous areas, you can get more detail when you go to higher resolution. Typically, for some of these advanced versions of the model, we can run on roughly 700,000 processors at a time for some of the extreme calculations. For the lower resolution models, we consistently run 2 or 3 or 5,000 processors at the same time. So I think that we're learning how to scale our calculations so that they run fairly efficiently on the new generation of computers. The vertical grid system sort of looks like this, where you have pressure levels at the top, and you transform the grid to follow the mountain shape in the lower levels, and so that when you get up to the stratosphere, it becomes pressure levels. So these are what we call hybrid systems, and it works pretty well. It's not completely free of computational problems, but I think most of the modeling groups have adopted something along these lines. Now, if you look at something in detail, like such as the land surface model, we keep a track of several species of plants. That we have heat that goes into the ground. Do we have sand or soil or clay or organic? And we allow that to be specified as a function of the place, of the geographical place. We keep track of all kinds of the radiation treatment and take into account on the shadowing effects of the vegetation on the ground and so forth. And we have hydrological cycles which sort of take into account precipitation, some of it falling on the leaves, transpiration from the leaves out to the atmosphere, sublimation, melting of snow on the surface. We have our root systems, aquifer recharging in water table. Over here on the biochemical cycles is still an area of very active research where you keep track of the leaves coming out in the spring and then dropping down and evaporating moisture off the leaves, either on the ground or on the vegetation, on the roof grow. And then in some of the versions of models, we have nitrogen fixation and on leaching. So all of these processes are now treated in a much more the realistic, including fire, frequency of fire essentially based upon drought conditions and so forth. So all of these are, and these fires can be started by man or of course by lightning sources. So you can think of this as a very interactive system. Here I want to show a very high resolution 10-kilometer ocean, world ocean. Here you're seeing on the Gulf Stream off the east coast of the U.S., and the Gulf Stream moves up along the east coast and then meanders into the North Atlantic, where you actually get some of these gyres separating from the main current, and it's quite realistic. The same thing is true off of the coast of Japan, on the Kuroshio current. Equatorial waves, El Ninos, can also occur too if the water piles up on the western. Then you get a Kelvin wave of that water flowing back at the surface. So all of these features show that if you go to high enough resolution, you can get very realistic ocean currents. And I think this is at a point where we have a pretty good understanding of how the oceans work now. In the early days, our ocean models were very coarse resolution and highly diffusive, and now we have more realistic ocean currents. And you can see here, for example, in the fall, in the winter, on the oceans get cold in the northern hemisphere, and they warm up in the southern hemisphere. So you get this sort of heating up and then cooling in both hemispheres. So here again, great progress has been made in the oceanographic community. Here I want to show a NASA showing aerosols. On these white aerosols up here are sulfate aerosols caused by the burning of fossil fuels, mostly coal. And sometimes on these filaments of aerosols go all the way over to the Europe. Also off of the coast of Japan, you can see aerosols. They're very highly concentrated in these white areas here. And some of them come over to Hawaii and to the western coast of the U.S. And embedded on you also see hurricanes and cyclones. Here on you're looking at aerosols caused by dust off of the Sahara Desert as it moves across the Caribbean into the Caribbean states and in the southern part of the U.S. On the green ones here are organic black aerosols from the burning of vegetation in the Amazon and in the Africa. And then down here, these are dimethyl sulfates from the sea spray off of the ocean, and showing how that sea spray aerosols get mixed into the circulation of the southern hemisphere. So typically now we can get very realistic aerosol distribution by having them embedded in our climate models. And I think you'll see more and more emphasis on trying to figure out the role of the aerosols and how they influence climate. Here's from some work of the Michael Werner of the DOE LBL laboratory, where he looks at on the 25 kilometer grid a version of the model. And I want to point out that we hope to use, as I said, on this resolution in our next IPCC assessment, which is coming up in a few years. Over here we have tropical storms, and when you use high enough resolution, when you get down to 25 kilometer, you get hurricanes and tropical storms. We didn't get these before in our more coarse resolution. We use a 1 degree model, which is roughly 100 kilometers. We didn't get tropical storms and hurricanes, but when we go to high enough resolution, we can get them. And you can see on the observations are here, and the model is down here. So you get very similar patterns in the Pacific and the Atlantic Ocean for the tropical storms. When you move to the hurricanes, this is the observations up here, and this is the model down here. And remember, the difference in tropical storms is somewhere around 75 miles an hour, sort of wind speeds. And it gives you some idea of the intensity. And so that we do a fairly good job of actually simulating that in the places where we should find them in both hemispheres. Then over here on the very intense hurricanes, I forgot the definition of an intense hurricane, but probably something of the order of 100 miles an hour wind speeds in the storm systems. We also do a fairly good job of capturing those. So now this is in a version of the model where we put in the observed ocean temperatures. Now when we couple the ocean and the atmosphere, and we don't get as good of a distribution because the model has some biases. And we're working on trying to reduce some of those biases in our coupled experiments. Another major feature that we couldn't get in the early days, but we're capable of doing now is El Ninos and La Niñas. And you remember El Ninos are the unusually warm temperatures in the equatorial eastern Pacific, in this region here where they have a little box. And that's on the red lines here. And the reverse of the El Nino is the La Nina, and that's the cooling in this tropical box in the central Pacific. And here's the observations. This is the observations, and here is the model simulation. So you get a very similar pattern, and the frequency and the period in which these are more prevalent is pretty close to the observation. So this was a major sort of breakthrough about 10 or 15 years ago that we can get models that reproduced on the El Nino and La Nina events. I know that you guys here are hoping for El Nino. And it looks like, from what the observations are showing, that we should be getting into an El Nino on this fall and winter. So hopefully you can get some rain here in California. Now for the ice sheet modeling, we haven't really coupled it in yet, so we have standalone versions. Here's on the flow of the major glacier areas in meters per year. And you can see that you have these major glacier flows going into the Atlantic in certain regions. And here's the simulation of a standalone version of the model. And we do a pretty good job. And this is work done primarily at the DOE laboratory of Los Alamos. And so I think we're getting close to the time of actually simulating this. And now we need to do this not only for Greenland, but we need to sort of do it for Antarctica too. And I think that will be another milestone for climate modeling. I want to show just a couple of examples of the research in which we're sort of doing here on the NERSC computers. First of all, in the last IPCC assessment, we carried out many of the simulations here. And we actually do ensembles of simulations. If we're looking at just one IPCC scenario, we would do sometimes 5 or 10 ensemble members to get some range of the variation in between different members to give us some idea of the standard deviation. And we also carried out a number of single forcings where we just put in the volcanic eruptions or put in just the greenhouse gases or the solar variations or the black carbon, and that we could sort of do a sort of detective analysis of what's causing what in the changes of our climate. And that's been very valuable because the researchers really want to not sort of unravel what's causing what and having ensemble members of different forcings. And so we call those sort of single forcing simulations. And then we look at the effects of hurricane changes on the closing of the Bering Strait, heat waves, and model development. And so NERSC has been a very important component in giving us the capability of unraveling more of the mysteries about climate change. Here I just want to say something about heat waves. And this is a paper that got a lot of attention about 3 or 4 months ago. It turns out that we identified a very interesting pattern in the climate system that people have not exploited, and that is there often is 5 waves in the northern hemisphere at different times of the year. And that 5-wave pattern is what we call a Rossby wave, and it actually goes not from west to east, but from east to west. And that wave gives us some advance warning of when we're going to get a heat wave. If that wave, which is slowly moving in this direction, going towards the west, if it is in such a position where it causes a bulge in the jet stream, it can cause a stubborn heat wave that can last of maybe up to 15 days. And just knowing that sort of what that pattern is, it gives us some warning about when the next heat wave might arrive. And the forecasters hadn't even known that this was possible. But now we wouldn't have been able to see this unless we were able to carry out long-term simulations and repeat them with small perturbations just to sort of see, are there some permanent features in our circulation? So it's always nice to find something new that we didn't know before that could give help to society. Here we've carried out some experiments of closing off I won't go through the details of this, I won't have time, of closing off on the Bering Strait and ask ourselves, if the Bering Strait is open or closed, is that going to make a difference in the climate? And it turns out that there's a circulation system where on the Gulf Stream, it brings warm water up from the tropics, and then it sinks, and that water then goes towards the tropics again, and you have a kind of a big heat engine going on. And if you have the Bering Strait opened or closed, makes a big difference in terms of how that circulation gets set up and can possibly change. So we have better insights on this. And this publication also attracted a lot of media attention. And we also understand better on the interaction in between the Pacific and the Atlantic seesaw in terms of the Bering Strait being open or closed. And that was another paper that came out of this. Now here we show on the various scenarios in terms of the climate in the future. I want to point out on this RCP, a representative of concentration scenario 8.5, is what happens if you do have no change at all in the way that we emit carbon dioxide and other greenhouse gases. And we're at this point right now, and as far as we can see, on the future for us is that if we don't do anything, that we're going to warm up the climate enormously, like maybe 6 or 7 or 8 degrees, depending on what we do at the year 2100. So there's a lot of concern about how will the climate change. And so this is the worst case scenario. And here's on the RCP 6, and this is 4.5, and this is 2.6. All of these are made up in various ways, and I won't go into sort of detail about it, but if you run the 2.6, you have to find a way to take the carbon dioxide out of the atmosphere, and we haven't figured out how to do that yet. Planting trees won't be good enough to actually get to the 2.6. But you can see it actually has to take down the concentration if you had that. So it's what I call this negative emissions. So there's a great deal of interest in each one of these scenarios, but the bottom line is that we're on the path of this blue line here going all the way up, unfortunately. And the concentration that we're at is roughly 400 parts per million. And if we didn't do anything at all, in a few centuries, we'll be up to 1,800 parts per million. I don't think that the public's going to stand for that at some point. Environmental justice, this is where we interact with social scientists. And social scientists can, and I put this face of a child up there with the globe painted on him to kind of point out it's not us that will probably be affected. It'll be the next generations who will be affected by the climate change. Now, if you burn up a molecule of fossil fuel and put the carbon dioxide into the atmosphere, that molecule stays in the atmosphere of the order of 100 years. And some of those molecules will be removed on the order of a year. Some of them will stay in the atmosphere for 500 years. So 100 years is the average lifetime. So the reason the concern of the scientists who are involved in climate change is that if we don't do something now, then you've already built in a certain amount of warming, and because you can't immediately turn this around. It can only be done gradually unless there's some miracle solution to cutting emissions. And I think climate models can help in giving objective advice on the possible impacts of climate change on food production, flooding, droughts, sea level rise, health, and as well as decision support if politicians want to listen. Higher resolution and more complete models will help even more. Just want to explain a little bit about the political process here. Who do you trust the most? Military and medicine, the scientific community are fairly high. And if I jump down here on the press, banks, and Congress are pretty low. I don't think there's any great surprise there. And there's a great deal of debate going on. I listened to a little bit of the president's speech this morning about foreign policy, and one of the issues that he talked about was climate change. And the military is very concerned about this, but some of our politicians are not. The military knows that as climate change proceeds, there will be lots of pressure when people can't live in certain places like Bangladesh, or they don't have water or the resources. That's going to put a strain on the relationship between certain countries, and that's going to affect national security. And I think clearly this is something to really worry on the decision makers about. I might want to show that things have changed in some ways. During the President George H.W. Bush, shown here, he had a chief of staff, John Sununu, John Sununu has actually got a PhD from MIT in electrical engineering, but he also knows a lot about fluid dynamics. He misquoted me in a Newsweek article that because I ran one of the first couple of models of climate change. It was a couple of atmosphere ocean model, I should say, and sea ice model. When I discovered the article in Newsweek, I sent him a telegram saying, I don't think you quite got it right. He called me up on that evening after the article came out, or after I sent the fax. And the first question he asked me, which was rather strange, as chief of staff of the White House, are you using finite element or finite differences or spectral methods? I knew that this was not the normal interaction with politicians. And we had he said, how can I learn more about climate modeling? He said, I'll send you a copy of the book I wrote. I kind of wrote a textbook on climate modeling. And this is 1989. And sent it overnight mail. He called me up the next day and said, it hasn't come yet. I said, well, we sent it in FedEx. And then he said, someone's in trouble over here. Now, for anyone who knows John Sununu, he's a tough bird. I thought he had other things to worry about than worrying about climate modeling. He's supposed to be sort of running the government. Well, anyway, he invited me to come back well, let me go to the next person here. Oops. On this person is Alan Bromley, the President's Science Advisor. And he called me up a few days later and said, could you come to Washington? But I can't give you, I can't tell you on what he wants. Well, I went like a few days later, and I went into John Sununu's office, and he said, I want a climate model I can run on my Compact 386. I said, we don't have models you can run on your Compact 386. He said, I have a Fortran compiler. Now, here again, I thought he would be too busy to want to run a climate model in his office. But anyway, when I left the office, Bromley told me, just ignore him. He's all exercised about climate change. And then a couple of weeks later, Bromley called me up and says, could you get him off my back and get him a model you can run in his office? So what we came up with was a one-dimensional model, and we tested it out on a Compact 386, and we got it so it would work. So he was able to carry out some experiments. And I'm not sure we ever convinced him, but one of the interesting things about this exercise was that administration had a meeting and invited me and another scientist to come to the White House and speak to the cabinet about climate change. And at the end of that meeting, I have to admire Alan Bromley, the science advisor. He went around the table, because we had the head of all of the science agencies, and asked them, do I have your commitment to produce a program to do research on this very important problem? And they all said yes. And that was very important. If you know how on the bureaucracy works, you can get the head person to make a promise, then it's easy to get things, to make them happen. And out of that came on the U.S. Global Change Program, and that is now $2.7 billion. Involves, actually it's 13 agencies, and it's coordinated out of the Office of Science and Technology in the White House. And it's produced a lot of very important research. And it funds on the Department of Energy's program in this area, NSF, NASA, and so forth. The biggest amount goes to NASA for the satellite programs dealing with Earth science. So anyway, a lot of progress has been made over all of these years. And I chair on the review committee of the U.S. National Academies to help guide on the U.S. Global Change Program. So, and what is interesting about this to me, looking back, is that on the objectives are very good. I mean, this was put into law, into the Congressional Act of 1990, and it's really carried us forward in improving our understanding of climate change. What's remarkable also is that it was bipartisan, but it's not bipartisan anymore. One party believes in climate change and another one doesn't, and that has been very unfortunate. So in this area of research, especially on the House side, we're seeing cuts, small cuts in the climate change. And I think part of that's just driven by the fact they don't want to hear the news that comes out of this type of research. Just very recently, the National Climate Assessment was released on May 6th. I had the pleasure of being at the White House for that event. And it's 1,100 pages. It gives all kinds of advice to city planners, state, and gives it's broken up in terms of different sectors like energy, food, agriculture, and it gives a lot of advice on the latest of our understanding of what climate change will mean to different sectors in the population. I'll end right there, and I thank you very much for inviting me, and I'll be happy to take on questions. Thank you.
We do have over 100 people watching online, and we're also recording this. So what I'd ask is that if you just raise your hand, I'll hand the mic to you for questions. So any questions?
Have I scared you all?
So one question I had was, you talked some about ensembles of calculations, and as you look to the future, do you see a greater need for uncertainty quantification running large ensembles, or is the greater need for more fidelity in the models?
I think we want both.
So.
But I think the strongest need is still in ensemble size. Mm-hmm. Because as we look for, if it's a major event, such as a huge volcanic eruption, you don't need a very large ensemble size. Mm-hmm. We can identify its effects. Mm-hmm. But for the moderate size events, such as mid-tropospheric aerosol, the black carbon aerosols, we have trouble separating on the effects of those type of aerosols from the natural fluctuations. Mm-hmm. And so we need an ensemble size of something of the order of at least 10 mm-hmm. to separate. For that heat wave thing that I mentioned up earlier, we needed somewhere around 30. Mm-hmm. So it depends on the magnitude of the forcing versus on the natural mm-hmm. fluctuations mm-hmm. In the model. And so it's separating the signal from the noise. Mm-hmm. It's no problem, of course. Mm-hmm.
Dr. Washington, thank you for your presentation and for your work. My name is Jim McMahon. Lots of your work has focused on the global and then national advice, but national governments so far have not taken a lot of climate actions. Do you see opportunities as the resolutions improve for subnational entities, states or cities, to take advantage of this in their climate planning?
Yes, and that's what Yeah, I think that's an example of where if we have higher resolution, we can really give more precise information. But still there's going to be a high level of uncertainty. The reason is we don't know which way the world's going to want to go. If it doesn't want to cut back on emissions, then we're going to get the worst case scenario. So we explain this in the National Climate Assessment for the regional and the local governments. So if you look in that document, if you live on the coast, say like in Florida or in the off of the east coast of the U.S., they're going to want to know how high of a seawall should I make? How warm is it going to get? How are the changes in the corals and the other things in the ocean going to change? Or if you're going to have species disappear as they move up in the mountains, but you can only go to certain species can't exist when it gets too hot, and it's going to affect not only animals but vegetation. So we hope to have in this document enough information so that you can sort of figure it out for that local community. I might want to point out that also just came to mind. Given the experience with on the rollout of the Obamacare, we were quite concerned about how good can this website be set up for, because it's not going to be a printed document. It's 1,100 pages, but it's completely internet document, so that you can go to a section, and if there's a word in that section that you don't understand, you can just click on it, and you can find the definition of it. So it's easy to sort of use. What we did was we released that document almost 6 months earlier in draft form, so that if there are any glitches, we could catch them and correct them. So it's gone through a lot of review and so forth. So hopefully it gives good advice to people on the regional and the local scale about climate change and its effect on our infrastructure as well as society. So I think it'll be a very useful document.
Hi, I'm Norman Barasa at the Building Technologies here at LBL. I do a lot of work with weather data for building modeling, and I work with a group at the ASHRAE. And there's several of us that are mine's resolution related, my question, on the 25-kilometer grid resolution that you've selected. It's suspiciously close to some of the actual meteorological year methodologies that we're working with, specifically Richard Perez at the SUNY New York University up there, uses a lot of satellite data. What are the factors that brought you to 25-kilometer grid? There might be more than you can list, but the significant factors.
Yeah, I think for the last IPCC assessment, most of the models were running with roughly 100 kilometers. We can probably go down to something like 10 kilometers, and we have some experimental runs where we do that. The problem is that we can't do ensembles with those. We can only run a few experiments, and that's a limiting factor. So there's a compromise in between, looking for a sweet spot in between really high resolution but only a few experiments, versus a somewhat lower resolution and being able to do ensembles. As I said, it would be very nice if we could do something like 10 ensembles, and then do lots of different experiments. Forcings turned off and on and things like that, so we can unravel things. So it's a sweet spot compromise.
Hi, I'm Brian Nord. I'm a cosmologist actually visiting from Fermilab. I'm wondering if your models are able to take advantage of subgrid simulations to improve efficiency, sort of like adaptive mesh refinement.
Yeah. We have that capability, and there are several groups or subgroups who are actually carrying out some subgrid calculations. But one thing that we've found out consistently over the long history is that when we go down to smaller and smaller scales, the parameterizations break down on the way that we parameterize radiation, cloudiness, and so forth. So that we haven't reached a point where the solution stays essentially the same. So that means that the subgrid scale phenomena is still very important, and that we need to get improvements in our parameterization so that they can automatically scale. But they don't scale now. When we put in our highest resolution, say at 10 kilometers, we still get, cloud systems. We don't get individual clouds. The same is true with vegetation. We have to deal with a community of vegetation on that scale, but we can't really say much about the subgrid scale. We have to specify that. So there is some challenging things when we get down to the real grid scale. And keep in mind, if you're looking at waves, on the waves have to be several times larger than the subgrid scale or the grid scale in order to resolve them well. So there's some, even when we look at our hurricanes and tropical storms, they're not perfect because we're not taking into account the actual details of how the cloud systems work. So we have a lot to learn, I guess is the way to put it.
I was wondering if you could comment on the increasing number of sensors and detectors that are available for and how those influence the climate models. For example, I've heard about laying sensors on the ocean floor and how those might be incorporated into future models and using measured data from the atmosphere or the ocean.
Now you're talking about what, sensors in the ocean or the atmosphere?
Yeah, water sensors in the ocean.
Well, there's been a tremendous breakthrough in these things that are called the Argo floats. Have you heard about those? Argo floats have given us a tremendous understanding of how the upper ocean works. It's where you have these floats that essentially go up and down and transmit on their data to a satellite. And they've given us tremendous information about the upper ocean and how it interacts with the atmosphere. Up until then, we just had a few ships a few times a year going sort of north and south or different tracks and giving us a little bit of data. And we didn't really know how to treat the upper part of the ocean. And now with this system of Argo floats everywhere in the world's oceans, we can really understand the oceans a lot better. And I don't think that we still have a good observing system for the deeper part of the ocean, the bottom. Unfortunately, we have to still rely upon occasional ships that go back and forth, doing these surveys. But maybe over time we'll have a more regimentized observing system, because the Argo floats in the ocean are very similar to all of the weather stations in the atmosphere. We can almost do a daily analysis of the state of of the oceans as we do with the state of the atmosphere from sort of weather observations. So it's been a big breakthrough in the last 15 years.
Well, let's thank you again for a wonderful lecture and coming out. We really appreciate it. Thank you very much.
Thank you.